All right, so we're in 12.1 today. A reminder, your test is tomorrow, so then we'll deal with 12.2 on Thursday. We are not going to be moving fast through this chapter. We have like a dozen units in this chapter, or like lessons, whatever you want to call it. So your mastery is far away. We'll take a couple quizzes throughout the chapter to just check in points. And you'll notice today's homework's the K version. I am starting to like look pretty critically at the version. So instead of just doing evens odds, it's easier for me really to just give you the K version of the homework. So you'll notice that there's only like 20 problems or something like that. So, if I drop this ball, obviously it's not going to bounce all the way back up. No. This is an orange. This is a ball.
Yeah, drop the orange.
So, if I drop these balls, compare them. Obviously we're not in a sealed system. We have air resistance, all that stuff. Whatever you're going to say, but what happens to both of the balls as they fall, or anything as it falls? A flower pot in this case. Grant?
It speeds up until it hits the ground.
What do you mean it speeds up until it hits the ground? Explain more about that.
As it's falling, gravity takes hold of it, and gravity makes it progress.
So, gravity takes a hold of things, and a lot of times we ignore any forces against gravity. Anyone know what the forces against gravity are?
Air.
Friction caused by the air, anything it might
Yeah, friction is like surface area.
Yeah, any surface friction. So if it's like sliding, there's going to be friction like that, but gravity still takes effect.
Other gravity?
Yeah, any other gravity. So other planets that might be close enough to affect us, the moon or anything. It's very small, pretty negligible. So, okay, so that's what happens when I drop something. But what happens, you paying attention? Kurt, paying attention? What happens when I throw something, when I arc something? So I didn't know how far it was going to be.
Boy, I was throwing higher than him.
There's a ceiling there.
Interference.
I thought you were asking.
So what happens? So gravity is still taking effect, right? So when I throw back, arc it. So throw. Well, I don't know if you can throw underhand with being back there. But what happens when we toss something? I guess better than throwing, when we toss it. What is going on? What's the relationship? What's happening? Leon?
The force, like, it's greater than gravity, and then gravity starts taking.
So I have to apply what? I have to apply an initial force. And then I have factors working against me. Gravity is working against me as the ball is in the arc going up. There's a point when it's literally motionless. It is a very, very short amount of time. But especially when we toss something straight up, you can sometimes see the point where it stops for a second and comes back down. And really, even if you throw something straight up, it's parabolic motion, because straight is really relative. Like, straight is very hard to actually make happen. So we already know this flower pot, as it falls, it speeds up. It goes faster and faster and faster and faster till it hits the ground, probably breaks. There is also, and we won't go far into this, there is also a terminal velocity. When you cannot go any faster, you know why terminal velocity happens?
Friction.
Yeah, when the acceleration on the object and the friction it fights against are the same. So if you drop like a quarter off like the Empire State Building, it will not continuously accelerate. It will hit maximum velocity, and it will then go at a constant rate.
Coincidentally, it'll also kill someone if it hits.
So if you throw it, it's already closer to its maximum velocity. So you can never go past, whether you drop it or throw it, you can never go past its maximum velocity. You'll get there faster.
But what if it's already falling?
And you hit it to make it go
Yes.
fast. It'll slow back down. If you throw it faster than its maximum velocity, it'll slow down.
Okay, but you can get it past, it just won't stay there.
Yes. Okay. So I guess I said that wrong to begin with. Good question. So, all right, we got to move on though. So we know this flower pot, we can simply, because it's only falling, we can say negative 16 t squared plus c. Now, what is this negative 16 here? Because there's two different ways we talk about gravity.
This is an object.
Oh, okay, so it's going down. So it's negative 16. Okay. Mackenzie? Yeah, well, okay, close. Leon?
It's like acceleration. It's acceleration.
Oh yeah, it is acceleration. So the negative is directional.
Yeah.
Don't think of negative as slowing down. That's the acceleration of gravity. So C would be where it started. So it started 64 feet up. So as we move through this stuff, don't know what I'm even looking for. We are really working with parabolas, but we start by dropping objects because it's easier to look at, but it still actually, when we graph it, creates a parabolic relationship. So in these forms, we have three different forms of a quadratic function here. My 3x squared, very simple. Just my x squared multiplied by 3. It's going to change the magnitude or change the slope. X squared plus 9, what do you think the plus 9 would do?
Is that just a 1?
It's a shift, right? So it's going to be some kind of shift in the graph. X squared minus x minus 2. Well, now we've got a square and a just single power and a constant. So we've got a shift happening. But the question is, what happens now that I have this minus x in here? And we're going to see that as we go through.
When does this turn to x minus 2?
No? What do you mean?
Well, because then you can split the x into 2. You can x times x minus x minus 2.
Oh, but those still would have to be grouped together. And they're not like terms because the x times x cannot be broken up. You can't subtract away because they're not like terms. Good question, though. So this is really what we're going to see. We've worked a little bit with solving quadratics, and we're going to do more of that this chapter as well. So vertex. What's a vertex on any polygon, any shape, anything that we're talking about? A vertex is always a point where... Greg? I don't know if that's a hand or if you're just...
Two raised lines. Yeah.
Yeah, I agree in a way. It doesn't have to be two different lines, so that's why I'm kind of like hesitant to say yeah. You can really refer to it as a line, but it's what happens at that point.
Where they meet.
So if I consider this one line, and this point where they meet is the vertex, what's happening to the line? It's changing direction. So the vertex is always where something changes direction. So if that was hard to remember, you want to on your paper write change direction. Vertex tells you you're changing direction. So in a parabola, like when I throw an object, it's going up until it stops going up, and then it's going down. And there's a momentary point, a blip, where it's motionless. It's not going up or down, it just hesitates there for a second. So in my graph A here, what would be the vertex? Where does it change direction? Ben?
At the y.
At the y-axis, right? So this point is actually going to be 0, 3?
It also
Yeah.
says that line.
Yeah, because on your paper I gave you the answer. But B, and then the third one, which isn't really C. B you got to do on your own. So where does it change direction in B? Question?
No,
Isn't
no,
it like-
hang on.
Isn't the whole thing changing direction basically?
So if I look at this, if I go left to right, when we look at domain and range, I go left to right. So if I were to write this out in a table, I like your question. I do. It's just,
Domain is x, right?
yeah, it's alphabetical, domain, range. So if I were to put this in an XY table, I look at x at negative 3, y is, I don't know, it looks like negative 1 almost. If I look at x at negative 2, y is like positive 2. If I look at x at negative 1, y looks to be like 2.8. We could guess something close. If I look at x at 0, y is 3. And then if I look at x at positive 1, it starts to go down. And now I go back to that 2.8 value. And instead of going up from negatives to positives all the way up to 3, I now start to go back down. This point here is that pivotal point where it changes direction. So if I look left to right and I look at the domain and the range, that's where instead of the y increasing, it starts to decrease. Does that help? Because we're going to look at tables here in a second too. Ben?
Answer for the next one.
All right, let me capture this.
I had it before me. I was looking before you.
Ben, what's the answer?
Negative 1, negative 1.
That's the next
Wait, 1, negative 1. Sorry.
1, negative 1.
He's amazing at
Because that's where the parabola goes from going down to going up.
What? Okay, fine.
Class, the third one, the vertex is -2, -3. Now you will also then be asked if it's a maximum or a minimum. Now any quadratic is like infinitely large. It either goes infinitely far up or infinitely far down, but there's always a point where it's either the very bottom of the graph or the very top of the graph. So this is a minimum, obviously, because it's the lowest point we see. My previous points, here would be a minimum. This point would have been a maximum. So know how to identify whether it's a minimum or a maximum. Is it the topmost point on the graph, or is it the bottommost point on the graph?
So it will always be like on the Y.
No. These are only on the y because they're simple parabolas. And actually, this is not on the y-axis.
Yeah, that's not on the one.
Like B and R got it, we're not on the y-axis. So it all depends on what shift has happened to it. So if we think about linear equations, y equals x, right? It's just the line y equals x. What does +3 do? Shifts it up, right? Changes the y-intercept. Same thing if I had y equals x squared. That y equals x squared is the simple parabola centered at the y-axis, but that +3 is going to create a shift. But then there's also left and right shifts that happen, as you can see, because this has been shifted left and down. So we'll see more. Stay with me. There's a lot to get covered. All right, so now we look at graphing a parabola, and when the only thing that we're given is the function, I just create an XY table to figure out what the graph is going to look like.
In this problem,
So I start with my 1/3 x squared, start plugging in the three values it gives you. It gives you x equals 3, or x equals 0, x equals 3, and x equals 6. So plug in those values and find out what is the domain, or sorry, what is the range at that domain. I gotta find the right point to stop here.
what are good values to choose for x when making the table? Choose values of x that make x squared divisible by 3, so that the y values will be integers.
Hint on your paper, but why do you think I started at 0 and only went positive? Because every parabola is reflected across this axis of symmetry, so I can just reflect those points on the other side of the axis. Now, does anyone have a guess what the 1/3 is going to do to my parabola? Not nothing. It can't do nothing.
I thought you meant to the 0.
Oh, yeah, Grant.
Move it right 1/3.
Nope.
Is it gonna make it is it either gonna make it steeper or flatter?
When you have a multiplier to your x squared, it changes steepness. Either makes it wider or makes it skinnier.
Which one does which?
Exactly. You're on the next question now. So when I plug in 0 here, 0 squared, 0. So times 1/3 is 0. So that gives me the point 0, 0. So this one's going to be a nice parabola centered right at my origin. When I plug in 3, what do I get for the y value there? What's 3 squared? 9.
3.
What's 1/3 of 9?
3.
Yeah, so we get 3 in the end. Hey, we don't use the R word in here. So then 6 squared,
36.
1/3 of that.
12.
So now when you go to graph this, we just said that we have 0, 0, or sorry, 3, what was that, 3, 3? And 6, 12.
Yeah.
So we graph my 0, 0. We graph my 3, 3. Now notice this graph goes by 3s. And 6, 12. And because we know that squaring a negative value is the same as squaring the positive value. This 3 is the same as if it was negative 3. This 6 is the same as if it was negative 6. So we can just reflect those points across the line of symmetry, which here my line of symmetry is the y-axis. And then I connect them and make my parabolic shape.
It's a V.
Kind of like a V. It shouldn't really have a point to it. It should be a little bit more curved. It's just hard for me to do on the smartboard.
Oh yeah. Oh yeah.
So in this situation, it's the y-axis, but in other situations, it would just be the axis of symmetry. And that we figure out based off the minimum or the maximum of the parabola. Because here, I have my minimum point is 0, 0. So that also tells me my axis of symmetry is at x equals 0. Questions on what we just did? Try graphing the function in the got it, negative 3x squared. So now instead of doing 1/3, we have a negative multiplier. So well, what will happen if we have a negative multiplier?
What does it mean by what are the domain?
Domain and range is x and y values. So for domain and range, I would start by a nice little xy table. Because I know that my multiplier in front just changes steepness, I again would start with 0 and then decide what other values to use. Well, since it's got a number instead of a fraction multiplier, I would just start slow. Do like 0, 1, 2, 3. And very quickly, you should see we get very negative. That's why I did not give you very much of the graph. Once it runs off the graph, we just put the arrows. So when I start graphing these points, I got 0, 0, 1, negative 3, and then 2, negative 12. Well, that would be way down here. So it runs off, even if I had put the 10 by 10, because initially I plugged a 10 by 10 in here, it wouldn't fit. Like, you still can't fit that point on your 10 by 10. So I connect these, and then I mirror it on the other side. And you just draw the arrows to say, yep, it continues on. I can't draw the whole thing, so I just stop there. Questions?
Your other arrow goes past negative 2.
No, my apologies. Still very close. It's hard as they get closer in. It's hard to figure out. So this leads us to problem 3, when we compare the widths of our parabolas. Oh, hello. Capture. What makes it get tighter? What makes it narrower? Leon?
If the greater the absolute value of the coefficient.
Yeah, so the larger the coefficient, whether it's positive or negative, larger really, absolute value size, larger, makes it tighter. What's the negative do? Like negative 3, what was different about that as opposed to the 1/3? Jacob?
It flips the parabola around.
Flips it around. So here, I might note negative flips it. How do we want to phrase for the narrower or wider? So, so because we talked about a x squared, when a is larger, we get skinnier. You writing this down, Ben? And as a is smaller, or closer to 0, we get wider. So then for the got it, take those three functions and order them from widest to narrow. So what would be the widest graph up there in the got it? Should really just use cards. Kale, what would be the widest graph there?
2. Second one.
Here? So as A is larger, we get
I was
skinnier.
looking at the pictures.
Oh, you were looking at the first one. Yeah, if we move on down to the got it, where we don't, because when we see the pictures, it's pretty easy. But when we don't have the pictures, what's my widest there?
The third one.
The third one. So we start f of x equaling 1/3 x squared. Gentlemen, you're on roll thin ice. Every time I look around, you guys are looking at each other, not up here. I don't want to say that it's starting to get creepy, but it is.
That's negative 1/3, sir.
Ah, good catch. Now that would not change the steepness, it just flips it. So even if I forgot it, that really doesn't change the steepness. What's the next, the middle steepness there?
The negative x.
The negative x squared. And then my narrowest would be the bigger the number, the bigger the coefficient, the narrower the graph. Doesn't really worry that some of you are like not writing any of this down, because I can see whether you're writing or not. It's pretty obvious.
Why is it in different colors? Are you just bored of it?
Just to separate them,
Okay.
because if it's all the same color, sometimes it gets hard to see.
OCD much.
So now let's look at what does adding on those values do? What way does it shift it? Jacob?
So if in this situation, adding the 3, because if you actually like solve it out, adding the 3 just makes the y 3 more than the without the 3.
Yeah, so it increases your range by 3. Be careful with how we phrase things, because parabolas can lay down horizontally. So when we talk about like, well, we could still really actually safely say y-intercept. Really, when we add on like our b value, this does just change the y. So anytime we add or subtract a b value, it's a vertical shift. Because if we start to solve these, 0, 1, 2, 3, 4. Well, 0, of course, will be 0, but then this will be 3. 1 would be 2, but then this will be 5. 2 will be, 4 times 2 is 8, plus 3 is 11. 9 times 2 is 18. This is 21. And 32. And 35. So on the homework where it says to graph these, you can either draw your XY coordinates or your XY axes, or just grab a sheet of graph paper before you walk out of here so you have it and you can just staple it on your homework. So what would, like, we don't actually have to graph these. On your homework, please actually draw them. All you have to do is do 3 points and then reflect the points. But how would these graphs be related, Robert?
The range changes similar.
So they've got the same steepness. So we could say same steepness or same slope. Slope's kind of dangerous though, because it's constantly changing. Every single like bit of x that you move, your slope changes, gets steeper and steeper. But the second graph here will be what?
3 higher.
Well, yeah, the second graph will be 3 lower. So shifted
First graph will be 3 higher.
3
He said
lower.
second.
from first?
Well, I said first.
He says that.
Hey, it doesn't matter. He understands it. Notice how I'm moving on. Some of you really need to figure out how to just move on. So here's our following object model. I just want to introduce the lesson with this so you understand like where this math all comes from. So you have an acorn in a tree. It's 20 feet up. And we're going to figure out how long does it take to hit the ground. This sort of math is important in engineering and mechanics and all kinds of branches where you have to figure out because of gravity what happens. Question? Answer? Stop. You don't always have to have your hand up. I love it.
Yes.
But I just am not going to call on you all the time. So here's our function. H equals negative 16 t squared plus 20. Gives us the height of the acorn in feet after t seconds. What is the graph of this quadratic function? So again, I ask, why are we using negative 16? I know you haven't done really much with physics, but why are we using negative 16?
Is that gravity?
It is, yes, but we want to say it a little bit more detailed.
It's like the direction of gravity.
It's direction because it's down, yeah. And then it's the feet per second squared. So it's feet, actually, a lot of times you'll hear people say it's feet per second, because it's actually like per second, yeah, but second being time, not power. So this graph shows us that at first we start to fall slowly. As gravity picks up, we go faster and faster. So if we were to approximate how long this took, it takes about 1.5 seconds. Maybe a little under 1 point, or no, sorry, there's 1.5, so that's like 1.1-ish. If we plug in the point, this is what they're actually saying. If we plug in this point, we know that we've gone past our x-axis, so we know we're in between these 2 points somewhere. We could keep plugging in values and get closer and closer and closer, or if we use a graphing utility like our calculators, we can find the exact point of intersection, but it looks to be about 1.1.
You could just make h 0
Yeah.
equation and then you just solve the equation.
So if we make h of t, which really this should be phrased h of t, but if we make that 0, then we could subtract 20 from both sides. We'd get negative 16 t squared equals negative 20. We can do the division, and we actually get negative 5/4.
Excuse me, could I please
Or not
have
negative, sorry,
Isabella
positive.
Amelia to the office, please? Isabella?
And we figure out, well, what squared is 5/4, and we could solve that.
Square root of 5.
Yeah, so radical 5 over radical 4, so it's radical 5 over 2, which is still messy, but it is a way to get an exact answer. Questions? When we're trying to find when it hits the ground? Greg, can you stop playing with toys, please, dude?
The little pop-out thing from the graph, it's wrong. The height could be negative.
So, it says do not plot 1.5 negative 16 because height cannot be negative. Okay, I agree with what you're talking about. It depends on your reference point, but they're talking about when it hits the ground. So the acorn cannot go through the ground, is what they're saying.
The ground.
Yes, thank you, 8th graders. I know that anything I say, you want to turn it around.
No, that's
But the acorn's going to stop at the ground.
Yeah.
All right, solve the got it when it falls from 70 feet above the ground. So, like Jacob said, if we want to look at this at when it hits the ground, we can just make our height 0. Because we're saying our initial height is 70, the ground would be 0. It's our reference point. Then either draw a sketch or describe what the graph would look like. Doesn't have to be pretty, just so we know what it looks like. Yeah, I kind of did that out of habit. Because anytime you do a parabola, you normally put the arrow on. Put an X, terminates. This is getting messy fast. 16's not that bad on the bottom. It's radical 70 that's bad.
Radical 7 can't be simplified. Because it would be 7, 5, and 2.
We get approximately 2.09 or 2.1 if you want to round. So I make this 1 and this 2. My smart board's not cooperating. That hits just after 2. That's really all you would need. If I ask you to sketch a parabola, don't try to be too detailed. You don't have to label everything. You don't have to have 60, 50, 40. Like that doesn't matter. We just want to see relatively what's happening. It's a parabolic arc because it curves, it speeds up, gets closer and closer to straight. Hits right after 2. Any questions? Does this make sense? Okay, let's give it a shot. Yeah, there are exactly 20 questions.
Are we doing 20 questions
And
now?
so we have apparently we have
All of
Say
them.
references?
Yes.
We just do like the odd one.
I can give you the G homework if you want.
That should go live. No, you still have it. And French toast is good.
That's actually, did you know Gayatri last year? She was an 8th grader last year. That's her brother's book. Pranav would forget his head if it wasn't attached.
Oh, I know Pranav.